Well, I keep hinting at an electric circuit we want to investigate. If we take a generator instead of a battery and use that as the source of electricity to drive an inductor, a resistor, and a capacitor that are all connected in series in a network, what's the behavior of this circuit? Before we get to that, I want to compare what would happen if you take a generator and use it to drive just a resistor, or take the generator and use it to drive a signal strictly through an inductor. And to help relate to the behavior of those two circuits, I want to introduce something known as a phasor, or a phasor diagram. Now, a phasor can be thought of as a rotating vector. These phasors are really useful for analyzing any type of behavior that's sinusoidal. So we know that the EMF from our generator is a sinusoidal voltage. It's equal to a maximum value times either sine or cosine of omega t, and in household outlets that maximum value is 170 volts, which corresponds to an RMS value of 120 volts. Okay, so what are these phasors? Well, let's imagine something like the unit circle. Let's picture a vector in the first quadrant in this unit circle. That vector represents our phasor. We're going to make that vector rotate. And I want to imagine rotating that vector in a counterclockwise direction. So at some point, the vector is going to point here. And then at another point in time, well, you get the idea. Okay, so as it rotates around, its length doesn't change. In fact, let's think of it like this. Let's say that the length of that vector represents the maximum EMF. So in the case of a household outlet, that would represent a vector with a length of 170 volts. Well, the instantaneous value, the value of the voltage you get from the hot in a household outlet is constantly varying. So there's our neutral, there's the ground, and there's the hot. If we make a graph of the instantaneous voltage versus time from the hot wire, then it looks like this. So I guess this time I'm imagining it as EMF equals EMF max times cosine omega t. I hope I'm not confusing you by alternating between sine and cosine. It really doesn't make a difference as long as we express it as sinusoidal. It's just a matter of where we put our origin in time. Okay, so what does this mean? Well, at some random point in time, let's say here indicated by this dot, then there's a value of the EMF that's greater than 0, but certainly less than 170. Well, that might correspond to the instantaneous value of the EMF when the phasor is in this position. Here's what we mean. If you take the projection of the phasor onto the x-axis, that's the value, the instantaneous value of the EMF, right? So, in fact, this is probably a good expression then for the EMF. So let's think about it. Let's say at time t equals 0, the phasor is in this position. Then 100% of it projects onto the x-axis. And so at time t equals 0, the EMF is the maximum value. Now, if we go far enough in time that we go a quarter cycle, then the phasor is pointing directly along the y-axis, and it has 0 projection onto the x-axis. So at that moment in time, the EMF is 0. So you see what we're getting? We're starting with a maximum value of EMF. When the phasor gets to this position here, then we get this data point. when the phasor has rotated to this position, we get this data point. So what gives us this data point right here? Yeah, when the phasor has rotated to this position. So what data point are we going to get when the phasor has rotated counterclockwise all the way into this position? Well, we're projecting this far, right here, projecting that far onto the x-axis, and that corresponds to maybe that data point. And then the phasor rotates to here. We still haven't rotated a full cycle yet, so now that's our 0 point. And then finally the phasor rotates, and it rotates back to here, and we've gone back one full cycle, and we've reached the maximum value again. So those are all the data points we would get as our phasor rotates one full cycle. So that's the nature of a phasor. It's just a rotating vector, and it's a way for us to relate to expressions of sinusoidal behavior. Ohm's law tells us that the current, for a resistor, if I multiply current times resistance, that's equal to the voltage, or the current is just equal to EMF divided by R. Well, if the EMF is some maximum value times cosine omega t, then the current through my resistor is the maximum value divided by R times cosine omega t. So how about we think of it like this? Let's draw another one of these phasor diagrams. Okay, the unit circle. And let's draw a phasor for the electric current. So that represents this value, right? The length of that phasor would be EMF divided by R. So what would be the length of the phasor that represents the EMF? Well, it would just be R multiplied by I. So we can draw another phasor that points in the same direction, but it's just longer. It's the value you would get if you multiplied R times the length of the first vector, right? If I multiply the length of that vector times R, then I get the length of this vector. And then as those phasors rotate, they rotate together. So when the current phasor is in this position, the EMF phasor is also in the same position, it's just longer. So what we say is the EMF and the current are quote-unquote in phase for a resistor. So that answers the question of how would this circuit behave. The current and the EMF would both reach their peak values at the same moment in time. So for some instant in time, the voltage you're getting from the generator is positive 170 volts. Maybe we'll say that's the voltage you have at time t equals 0, because we're imagining it as a graph of cosine. So right here at t equals 0, our initial voltage is 170. Then after a quarter cycle, now the output of the generator for a moment is 0 volts. So what's the current through the resistor at that moment? At that moment, the current is also 0 volts. And then a little later in time, the generator has reversed its polarity and is now giving negative 170 volts of output. So what's the nature of the current? Well, if we say positive current flows this way, and at one moment in time the current was 0, then when the voltage is at its most negative value, then the current is at its greatest value in the counterclockwise direction. If you go another quarter cycle later, the generator is back to 0 volts and the current is back to 0 current. Okay? Whenever the EMF is 0, the current is 0. Whenever the EMF is a max, the current is a max, and so on. The current and the voltage are in phase in the case of a resistor. No surprise. Not the same for the case of a generator that powers an inductor. And here's why. this equation, Ohm's law, tells us that there's a very direct relationship between current and EMF. But the EMF of an inductor is not described in the same way. The voltage across an inductor is equal to L di dt. So again, let's draw a phasor for the current that's flowing through a circuit that has a generator and an inductor. So we know at some moments the current's going to be flowing clockwise, so we'll say it's positive in value. At other moments the current is going to flow counterclockwise. We'll call that the negative value. And there'll be some moments in time when the current is equal to 0. For sure, a graph of current versus time is going to be sinusoidal, and let's just assume that it's a graph of cosine. So we'll say I is equal to some maximum current times cosine omega t. We can represent that sinusoidal behavior with a phasor diagram. So initially, at time t equals 0, our current phasor points straight down the x-axis. So that's this data point. At some moment in time later, the current phasor has rotated to position number 2, and that gives us this data point. Eventually, our current phasor has moved to position number 3, which gives us this data point, and so on. Okay, well, the voltage, if I hook up a voltmeter and measure it across the inductor, I don't get the greatest voltage reading at the moment that the EMF is its largest value, right? If I is equal to I maximum, or maybe I'll call it I naught, cosine omega t, then di dt is equal to the derivative of cosine is negative sine, so di dt is negative omega I sine omega t. So if we were to graph that, and so the voltage across the inductor is equal to L di dt. So the voltage across the inductor is equal to negative omega L I sine omega t. So a graph of negative sine looks like this. So that means at time t equals 0, there's 0 voltage across the inductor. And then if we go a half a cycle into it, at that point again the voltage is equal to 0. And any multiple of a half cycle, we get voltages of 0. Okay, so it's after 1/4 cycle that the voltage becomes most negative, and at 3/4 of a cycle, that's when the voltage becomes most positive. So let's see, where should I draw in the initial voltage phasor? So again, if this represents the current phasor at time 1, and then this red phasor is the current phasor at time 2, and the blue one is the current phasor at time 3, what's the phasor that represents the measured voltage across the inductor? It has to start out with a value of 0 volts, and after a 1/4 cycle become most negative, and then again another 1/4 cycle later back to 0. It seems like then the phasor that represents the voltage across the inductor is 90 degrees ahead of the phasor that represents the current. So this would represent the voltage across the inductor at point 1? And then what about for point 2? There's the voltage across the inductor at point 2. And at point 3, which by the way represents how much? A quarter cycle into the rotation of the current phasor, then the inductor's voltage phasor would point here. Okay, so in general, if we draw a phasor diagram for a circuit that consists of a generator and an inductor, if we draw in the current phasor in green, this represents the instantaneous value of I. Well, let me be clear about this. The length of its projection along the x-axis is the instantaneous value of current. The true length of the phasor represents the maximum value of the current. Okay. Then the phasor that represents the voltage across the inductor is always 90 degrees out of phase with the current. This represents the maximum value of the voltage across the inductor and its instantaneous value at any moment. The reading the voltmeter would give you at any instant is represented as the projection of this phasor onto the x-axis. So we'll call this lowercase v subscript L. Some say that the voltage across an inductor leads the current by 90 degrees. Or in other words, the instantaneous voltage across an inductor is always 90 degrees out of phase with the instantaneous current in the circuit. Well, that's the nature of inductors, right? Inductors are governed by Faraday's law and Lenz's law, which says nature opposes a change in flux. So here we have a generator that at some instant in time maybe has 0 voltage. And so it's not trying to send current either clockwise or counterclockwise. It's not trying to send any current at all through the circuit. And then the circuit includes some inductance. And so now the EMF of the generator starts to build, and it goes from 0 and it's becoming positive, and it's trying to drive current this way. So before the current even becomes large, the rate of change of current is its greatest when the current is the least. Let's think about that. If a graph of current versus time takes on some sinusoidal shape, then at a moment in time like here, the current is a maximum value. But the slope to that graph, which would be the value of di dt, is equal to 0. Now let's look at a moment in time where the current is 0. That's when the slope of the graph is the most. And the voltage across an inductor is directly proportional to the rate of change of current. In fact, a magnitude is equal to the inductance times the rate of change of current. So when the current is the least, the rate of change of current is the most, and therefore the voltage is the most. So before the current reached its peak value, which came here in time, the voltage across the inductor already had its maximum value a little bit earlier in time then the current reached its maximum value. That's it. An inductor is always trying to fight against the rates of change of current. So it makes sense that the voltage across an inductor leads the current by 90 degrees. Okay. Now, there's something known as the reactance of the inductor. And think of it as the effective resistance. Think of reactance as being like resistance. It's not quite the same thing, but it is a quantity measured in ohms. Okay? So the voltage across our inductor is equal to, well, the instantaneous voltage is L di dt. And as we saw, that gives us omega L I sine omega t. Voltage across the inductor at any instant is negative omega L sine omega t. Which means the maximum voltage across the inductor is omega L I. So if we say there's sort of an effective agreement with Ohm's law, if V equals IR, then the effective resistance of the inductor is omega times L. But we don't call it resistance, we call it reactance. We give it the symbol capital X. Okay? So reactance, or what we call inductive reactance, X subscript L is equal to omega times L, and that's a quantity measured in ohms. Now let's check that out. Omega is radians per second, and inductance is measured in henries. So a henry per second is the same thing as an ohm. So we know radians disappear whenever we do dimensional analysis. This should all seem a little bit sketchy, but stay tuned for the next video segment where we'll draw a phasor diagram for the case of a generator that's connected strictly to a capacitor. And we'll introduce a quantity known as X subscript C that we call capacitive reactance. And ultimately, we'll build our way up to describing the circuit that combines an inductor, a resistor, and a capacitor together. And all of it will be explained with the use of these phasor diagrams and a discussion of the quantity of capacitive reactance and inductive reactance. So stay tuned, the big picture will be revealed. But for now, make sure you've copied in your notes the formula for how we calculate inductive reactance, and come up with your questions of what exactly do I mean when I say the voltage across an inductor leads the current by 90 degrees, and try to challenge yourself or ask more questions for me of what's the value of this phasor diagram, and how exactly did I figure out that the phasor that represents the voltage across the inductor is going to be 90 degrees out of sync with the phasor that represents the current in the circuit. It all might be confusing for now, but stay tuned.